All right. Hello, everyone. Welcome to the November 19th edition of our Wildfire Seminar Series. Today, we're hosting Dr. Feng from the Argonne National Laboratory, where she's a principal atmospheric and climate scientist. Dr. Feng is also a scientist at large with the Consortium for Advanced Science and Engineering at the University of Chicago. And she was, a while back, a postdoc at our near Scripps Institute of Oceanography. Her work focuses on global and regional modeling of aerosols, clouds, and interactions with climate change, air pollution, and she has done some really, I believe, seminal work in the area of wildfires. You know, wildfires, as we understood from the several seminars we have seen, occur at a natural rate, but climate change is increasing the intensity and frequency of these events. And then one of the questions I guess everyone is asking is whether there's some sort of a tipping point when these events are becoming some, reaching the levels of catastrophes, regional catastrophes. So I think Dr. Yan Feng's work illuminates a pathway there where she looked at a lot of big data and came up with some interesting results. So with that, I yield the floor to you, Yan.
Okay, thanks for inviting me. It's a great pleasure to speak to you all about our work on wildfire danger modeling at Argonne National Lab. So I would like to thank my colleagues at Argonne, Dr. Jolly Wang, Dr. Guo Yu, and Connor Akhali, and a former summer student, Emily Brown, for their great contributions to this work, which happened mostly in the last couple of years. So wildfire is one of the most devastating natural hazards in the US, and every year wildfires spawn across the country, especially in more recent years. So this animation shows from 2001 to 2012 the footprint of the wildfire activities in terms of their emitted heat radiation, colored by units of equivalent nuclear power plant output. So larger and more intense fire activities are indicated by the yellowish orange color. As you can see, severe and large fires mostly occurred in the western and southwestern US, occasionally also appearing in the southeast of Florida. The streaks on the right-hand side show the total energy emitted. Clearly, 2011 represents an extreme year for severe wildfire activities. So to look at more wildfire characteristics, we have compiled a 33-year fire dataset that includes any fires larger than 1 acre over the conterminous United States. We use CONUS. The data sources include satellite detected fires and ground-based reporting. On the left, our analysis shows different trends in number of fires with different size. The number of large fires defined as fire parameter larger than 500 acres, indicated by the gray dots, show a statistically significant increasing trend by 64% during the last 3 years. In contrast, the trend in all the fires, including the small fires, is actually negative, decreasing by 16%, although it is not statistically significant. So the map on the right shows the occurrence frequency of large fires in the last 30 years. Not surprisingly, most of the large fires occurred on the west, which is driving the increased trend of large fires in the nation. Central and eastern US are relatively less prone to large fires. It could be because most of the large fires, oops, I'm going too fast. So it could be because most of the large fire data are from satellite retrievals, which have problems in detecting small fires that may be prevalent on the east. However, it is interesting to note that some locations like northern Texas and some parts of the eastern US, such as Florida, do have large fires over 30% of the time when there is a wildfire. So this map clearly shows that the wildfire characteristics are quite different between the central eastern US versus the west US. So zooming into the western US, over 7 out of the 10 ecoregions colored by shown by different colors. There is an increasing trend in the last 3 decades of large fires with high statistical significance across a large variety of vegetation and surface types. In particular, Rocky Mountains in green and Arizona, New Mexico mountains in pink colors experienced the largest increases, whereas fire activities in Nevada in light brown color and Mediterranean California remain stable and even slightly decreased, although this data set is only updated to 2011. So in addition to the number of fires, burn area from wildfires is also important characteristics of the fire impact. The observed trend in the area burned has increased more drastically than the fire frequency, implying that the fires in recent years may have become more intense and severe, yielding a larger burn area per each fire. We also look at the fire season. So the left figure shows on average over the CONUS, the summertime from July to August is the largest peak, with a second peak in April and a third and smaller peak in fall during October and November. This could vary by geographic location. So we show on the right-hand side the most frequent fire season by location. Most wildfires in the Northwest, Southwest, Northern Great Plains occurred in summer, colored in yellow. Some locations, such as Southern Cal, in fall. In contrast, wildfires in the Eastern CONUS mostly occurred in spring in green color, or occasionally in the wintertime even, possibly associated with the dry down after snow melt and ahead of the summer rainfalls. So wildfires cause extensive damage to air and water quality and human health and infrastructure and ecosystems. So it is concerning that climate change may cause more frequent and intense wildfires in the future. There are several studies focusing on the Western US found that warming temperatures in springs introduces early snowmelt, which with reduced winter precipitation, it has led to longer summer dry seasons and drier vegetation. All of those things provoked more long burning large fires. So we identified 2 major key challenges. One is how do we predict fire danger in changing climate? That requires identifying and forecasting the relevant weather and climate variables in future climate scenarios. The second one we thought is how do we predict the fire danger so that the forest managers or utilities can make informed decisions on how to allocate the available resources, as the fire management could be a very complex task involving multi-scales. So yeah, so that's what we think is our main objective. To quantify the wildfire danger and activities, usually a continuous numeric or categorical scale based on weather conditions and fuel moisture was developed and is often referred as the fire danger indexes. For example, the iconic Smoky Bear campaign run by the US Forest Service for promoting the prevention of unplanned outdoor fires in the local communities. US Forest Service used fire indices to describe the wildfire potential, and such as they use the Keach-Barine drought index, and fire potential indexes have also been used by the US Geologic Survey. That's shown on the right for planning. And on the right-hand side figure, the high fire danger is indicated by the yellowish red colors for large values of the fire potential index is calculated. So in the first part of my talk, I will briefly introduce the five fire danger indices we have used, which are also commonly used in practice. I will introduce how they are derived, what they stand for. The first three are commonly used FDIs in North America. From left to right include the Kitch-Barron Drought Index, short for KBDI. The second one in the middle is the US Geological Survey Fire Potential Index, called FPI. And the last one on the right is the Canadian Forest Fire Weather Index System, short for CFWI. These indices depend on different sets of variables, as you can see. From left to right, more input conditions are considered. So KBDI only depends on temperature and precip, whereas CFWI also depends on fuel loading, relative humidity, and surface winds. And there are two more complex FDIs that we also investigated, ERC for energy release component, and BI for burning index. The calculation of these two indices follows the approach described by the National Fire Danger Rating System. Compared to the first three indices, these two indices account for more detailed and comprehensive calculations of the dead and live fuel moistures in particular. So BI also includes a spread component that depends on both surface winds and slope class, which ERC does not account for. The complexity will determine each indice's application and performance. I will discuss further in my second part of the talk. But first, I would like to use KBDI and FPI as an example to go through a few key data sets that we use for calculating these indices. So KBDI is a very simple drought index calculated as a proxy for the cumulative moisture deficit in the upper soil layer that needed to bring the soil to saturation. This example on the left shows that if assuming 8 inches as the saturation soil moisture, soil is 3 inches from saturation, then the corresponding KBDI is determined as 300. So large KBDI values indicate significant drought for higher fire danger. This applies to all the fire indices. Higher values are higher danger. So even for its simple formula, KBDI mimics water dynamics in the soil layer. So it's indicative of wildfire occurrences and spread potential, especially for those areas with shallow root systems, such as shrubs, trees, and grass, indicating that the KBDI is suitable describing certain geographic locations. And also because it's very simple and easy to use, many agencies actually use it for their monitoring. So this figure is an example of the daily predictions by US Forest Service. KBDI is calculated using the weather station data by them and then extrapolated to a graded map based on distance. So therefore, KBDI data are sometimes sparse over a large area of the country, can be poorly represented over locations where station data is not available. A significant deficiency of this method is that this data are not able to represent the Western US well because of the complex terrain. But Western US is most prone to wildfires. Another problem of this approach is that it cannot provide future outlook because we don't have observations yet. So to account for this, we use graded data sets generated from statistic or dynamic downscaling. This is just an example. Daily precipitation maximum temperature can be obtained from this data set called PRISM, which is available at a spatial resolution of 4 kilometers over the CONUS region. It utilizes the station measurements and a weighted regression scheme to determine the precipitation and temperature values in complex terrain by considering factors like location and orographic changes. And this just shows you an example, our method in contrasting to the US Forest Service calculations for the KBDI. This shows a 2011 Texas Bastrop County complex fire. our calculations on the right, and the US Forest Service map is on the left. So you can see our calculation reproduce the evolution pretty well, but also provide a much refined picture of the spatial gradient in KBDI, especially in the Northern Great Plain and Central US, where the weather stations are few, leaving lots of blank areas in the US Forest Service maps. So another example I wanted to show is the fire potential index. It is an indicator of the wildland vegetation flammability that incorporates both satellite and surface observations developed by the USGS. It is more sophisticated as it accounts for the moisture level of both dead and live fuel, in addition to temperature and precip. Although the fuel moistures of the live and dead fuels are measured in the same way, their moisture content could be very different, and live fuels contents much higher, as shown in the two panels on the bottom. For the estimation of the dead fuel loading, the US NF DRS fuel model map is used, which provides a 1 kilometer resolution fuel model map for different types of fuel, including, I think, a total of 24, something like that. Based on each of the fuel type, we calculate a time-lagged moisture content based on temperature, relative humidity, and state of the weather, such as precipitation occurrences and cloudiness. The quality of high moisture content in live vegetations is parameterized from the satellite observations of vegetation greenness, the so-called NDVI. It is readily available from the NASA satellite products. For example, we're using MODIS global products for the NDVI for the live fuel moisture content calculation. So such geographic pattern for fire danger is also predicted in our calculation for FPI versus the USGS daily products. Again, our data has better spatial coverage when the station data are not available in areas such as the Northern Great Plain. The differences in the FPI values are mainly due to the estimation of the relative greenness, which is the parameter representative for the live fuel loading. We have used the updated satellite observations. So FPI is shown in previous studies to highly correlated with the fire occurrences over the US Western coast. And it also has been used by some of the power utility companies on the West Coast with their own proprietary versions. So it is worth noting that of the 5 indices, CFWI and BI is another one, are the 2 indices that also considers the wind effect. Previous studies have demonstrated high correlation in interannual variability between the fire indices that considers wind with burn areas, particularly better at the global scale. So because of the different complexity, each indices will provide different aspects of the fire conditions. So this figure compares KBDI versus the CFWI in the fall on the left and the summer season on the right. The CFWI predicts comparably higher fire danger in the Northern Great Plain for the fall and summer than KBDI. Also for CFWI, summer risk is larger than fall, while KBDI is the opposite. So these kind of differences are more evidently on the regional scale. Here I'm showing the seasonal cycle of these 2 indices over the Northern Great Plain. So it implies that use of various FDIs could lead to different estimates of occurrences, onset and intensity, spatial extent of the fire danger risk. So it is essential to understand the factors that drive differences between these FDIs and to better evaluate and their predictions. So to do that, we calculated this global delta-based sensitivity analysis on 9 time vary input variables for the 4 more complex indices, excluding KBDI. Larger delta values on the y-axis indicate stronger dependence. So the top row shows the dependence of annual mean fire danger to input conditions. The bottom row shows for the extreme large fire danger defined as the calculated fire indices larger than its 95th percentiles. On top, daily minimum relative humidity in blue are identified as the most dominant parameters for FPI and CFWI, whereas daily precipitation in purple for ERC and BI indices. For extreme large fire danger on the bottom, the sensitivity analysis shows consistent results that the entire distribution of values, the dominating parameter is the minimum relative humidity. This suggests that the large fire danger potential depends strongly on the lowest relative humidity during the day, regardless which indices is used. For ERC and BI, which accounts for the dead, live, fuel, moistures the most comprehensively, the highest relative humidity during the day is also the strong factor in determining the occurrences of extreme large fires. In contrast, for estimating average fire danger, daily precipitation is more important. Also notably for the 2 indices, the second column and the fourth column, CFWI and BI that considers wind effects. Wind has relatively low influence on the mean fire danger in the top row, but increase the influence on the extreme values on the bottom. This is partially because the wind speed we use from the model and it's generally too low for triggering exponential effect of wind speed, except under the high fire potential conditions. So it is critical to forecast the episodic and transitionary high wind conditions for accurate fire risk assessment. So this sensitivity analysis indicates that the application of various FDIs, for example, high wind regions definitely use CFW and BI would be probably more applicable, whereas the FPI would perform better over the few sufficient regions as it accounts for the few types explicitly. So it is critical to understand the predictability of FDIs with respect to observed fire characteristics. There are lack of such investigations, and the validation of the FDI is often performed at regional and seasonal to annual scales, where actually fire monitoring practices require reliable metrics and assessments at different scales. So there's a critical need to assess the predictability as a range of spatial temporal scales over the entire CONUS region. So we examine the 4 calculated 4 fire danger indices versus observed wildfire activities for the last 30-something years. The input weather informations are from the UC Merced Great Met 4-kilometer dataset, and the fuel information is from NOAA, and also an FDRS fuel type map. The fire observations, we aggregated 2 datasets, including fires down to 1 acres larger. So a total of 1,803,000 historical fires were found to meet these criteria. And 4 FDIs were calculated at various spatial and temporal scales. And then we calculate the correlation between each FDI indexes with the historical fire size at 9 different scales. And then we further derive a linear regression model between those two quantities. So including the 9 spatial scales, including 3 spatial resolution from grade level at 4 kilometer to regional and to the entire country. The 3 temporal scales include daily, monthly, and annually. The total combination of the spatial temporal scales is 9. So in the following, we also divide the CONUS into the 7 regions to analyze. The divisions are based on the National Climate Assessment Recommendation. On the right, this example shows the density scatter plot on the CONUS and the monthly scales. Specifically, each hex bin represents the monthly fire size in the Y direction, corresponding to the monthly mean FDI on the x-axis. Both values are averaged over the entire CONUS. The color indicates the density of the data points. In this case, most of the data fit the linear regression line with a correlation coefficient of 0.72, suggesting that FDI is a good indicator of fire size over the large spatial context. Expanding this calculation to the other spatial and temporal scales for all 4 indices. Here we show 3 spatial temporal scales. The finest spatial temporal scale, which is grade level daily values, is shown in the top row, and the middle row is for the regional scale and monthly means. The bottom row is for CONUS and annual means. So larger spatial temporal scales, as you go down from top to the bottom, each column individually corresponds to a specific fire danger index. From left to right is FPI, CFWI, BI, and ERC. All calculated correlation coefficients shown on the top of each panel are statistically significant. Of all the 4 indices, the most sophisticated ERC, BI, and CFWI show larger correlations with observed fire sizes than FPI on the left, outperforming FPI on every scale in predictability. Between the 3, ERC in the rightmost column does a little bit better than CFWI and BI. This is interesting because BI in fact accounts for more factors than ERC, such as surface winds and slope influences on the fire spreading, supposed to be more sophisticated. But this performance is also, as I mentioned, related to the wind, the data quality, especially for the wind predictions from the model we use as input. So in addition, the predictability also generally increases with the larger spatial temporal scales from top row to bottom, indicated by a higher correlation and better linear fit between fire size versus FDI for the indices, except for FPI. FPI seems to do better on the regional and monthly scales. So the linear fit provides means for us to predict the future wildfire size using the calculated FDI, which could be calculated from the future climate model simulations of weather conditions. But first, we need to quantify the linear regression model in historical times against the observed fire sizes. The figure on the left is an example of fitting total fire size versus annual mean FDI over 7 subregions in the last 33 years. We use the fitted linear regression in black to calculate the annual wildfire size over the 7 subregions with 2 different input datasets shown on the right-hand side figure. The calculated fire size from the linear regression model is shown by the black dots using the observed weather variables, and by blue solid circles using the WRF regional climate model outputs. Both are compared side by side with the observed fire sizes indicated by the boxes and whiskers in gray. The comparison is reasonable for at least one of the modeled fire sizes, either black or blue dots over 5 regions, except for some underestimation by both in northwestern US and overestimation in the northeast. The differences can be attributed to the imperfect linear regression model. As you can see, there are some scatterness in the linear regression, as well as the uncertainties in the observed fire sizes could be too. Over most of the regions, using regional climate model WRF input variables are as good as observations, except for a little bit low bias over northern and southern Great Plains. In addition to potentially being used for predicting regional fire sizes, FDIs could also be used to look at the long-term trend in wildfire changes. As shown here, the 3 FDIs at the CONUS-wide annual scale in this figure show evident increases for the 1984 to 2016 period, consistent with what we have seen from the historical wildfire data. The simple linear regression is fitted to the average values of the 3 fire danger indices, reflecting a statistically significant increase. The shaded area is just the 95% confidence interval. So that brings up to the last part of my talk. How do we use the FDIs in predicting future fire danger changes? To assess the climate change impact on future fire activities, we use regional climate model WRF simulations at 12 kilometers to calculate mid and end of century FDIs in 2 future 10-year time slices, and then derive the differences from a 10-year historic time slice. The climate variables that we use are listed here, including winds, surface winds, relative humidity, daily maximum and daily minimum, daily maximum and daily minimum temperature, daily and annual precipitation, solar radiation. On the right-hand side is an example of the regional climate model simulated changes in number of days per year with temperature warmer than 95 degrees Fahrenheit by middle and late 21st century from Argonne's regional climate model simulations. This significant temperature increase will increase the demand of power delivery, for instance, and air conditioning uses that could further trigger the fire ignition. So the 12-kilometer WRF model does a decent job compared with the observation data for the historic time periods. This slide shows the calculated 95th percentile of ERC indices using the observed weather variables versus WRF simulations. As you can see, whether it's the geographic pattern, especially over the Western US, or grade level spatial temporal correlation showing by the scatter plot on the right, or the absolute values between these 2 calculations are quite similar. This supports the use of the WRF model outputs as an input to estimate the fire danger indices in future climate scenarios. Since ERC performs the best out of the 5 indices we have examined in the historical times. So we use ERC as a proxy for illustrating the climate impact on wildfire danger potential. First, we investigate the change in probability distribution of FDI, in this case ERC, in 7 climate regions over US. Blue is for present day, and red is for future climate scenario. We use RCP 8.5, which is a high emission scenario provided by IPCC for future. This is almost like the worst case that you can imagine for the future climate change. Future FDI in all regions is projected to increase in mean, which is shown by mu, and also variability standard deviation, and the upper tail of the distributions, implying that the wildfire hazard in future will be a more challenging issue to the nation. In terms of the changes in the mean FDI, the FGP, I just pointed this panel, and at northern east region show the largest and the smallest increases respectively. This is roughly consistent with the regional drought trends over the last 4 decades, published by a study by Feng et al. 2015. So most likely droughts and fires are going tandem. In addition, there is a larger variability in future FDIs indicated by the shape of the PDF, implying that the future values are more spread out to the 2 tails, smaller or higher values. In this case, the upper tail above the 95th percentile, that is shown in the inset graphs, denoting the extreme fire conditions, shows considerably increases throughout the CONUS over the 7 regions. What that means is that extreme fire in future will be more intense and danger in size of the burn areas. So this slide shows the changes in fire indices ERC for both median and 95th percentile values between the 2 climate states, each with a 10-year time slice. The mean fire potential on the left is projected to increase over most of the country, with the largest changes over the Southwest and West US, and smallest changes over the Eastern US, including Florida and Northeast corner. Excluding Florida, and because Florida and Northeast corner also have quite large changes. In particular, for the extreme large fire potential increases shown on the right-hand side, it's more substantially over the Pacific Northwest and Southwest US, extending to the Midwest part of that. Texas is one region standing out on both figures. It is subject to increased fire danger on both measures. The changes over the Southwest are statistically significant compared to the 10-year interannual variabilities. So based on the calculated 95th percentiles, we also quantified the changes in the number of days that exceed the 95th percentiles of the historic FDIs. The occurrence frequency of 95th percentile in terms of number of days is projected to increase by 30 to 80 days per year in the Northwest, Southwest, and Northern and Southern Great Plains. These increases are more than 2 times larger than their interannual variabilities, denoted by the dashed lines for statistic significance. Some areas, such as the western and eastern coastal areas, are projected to experience fewer than 10 days with FDIs greater than 95th percentile, the negative changes. So we're still investigating the contributing factors, but decrease in relative humidity in WRF projections associated with higher temperature and lower water vapor in those regions is considered as the main cause. Note that the pronounced increase of the fire-prone areas in the future compared to the present day values also include many parts of the central and southeastern US, which may not be as experienced as the Western US in handling the fire danger risk, especially needs to be cautioned. In addition, the Southwest US shows an estimated increase of 0.96 million acres, which is about 3 times larger than the present conditions in annual fire size, which is the fire influenced area. So we also broke it down, this number of days change by season. This slide shows in all 4 seasons, the number of days with high wildfire risks are increasing significantly by late 21st century, implying a prolonged fire season. This increase is especially significant in summer and fall over western and southwest US. It's important to note, although we calculate these fire indices using the future climatology from climate models, these indices can be also calculated for near real-time and weather scale forecasting in practice. Although there is a cautionary note that there are different uncertainties on smaller spatial temporal scales, as we have discussed earlier. The predicted fire danger zones are coincident with many regions experiencing poverty and high vulnerability, shown on the right-hand side, which could potentially exacerbate the fire risks due to crowded housing and limited transportation access. All the projected increase in the occurrence frequency and area can be attributed to climate change on extreme wildfire risks in our calculations. It changes the historic trend in the number of large fires. What we have seen in the historic trends in the number of large fires will also very likely expand toward the end of the 21st century. So at Argonne, we are also working with the resilience and grid modeling groups to translate the wildfire modeling for use in grid operation and optimization. The power delivery infrastructures can also cause fire and other hazards. A recent example is a campfire that have been ignited by an equipment failure, for instance. These kind of wildfire occurrences, including contact with vegetation or contact with animals, have not been included in our fire model, but this is an ongoing line of research that we are trying to integrate. So this is the example of the visualization tool that we are developing right now. The red colors indicate the areas with calculated near real-time high fire potential indices overlaid with the blue greenish red lines, which indicate the live flows in the power lines. Depending on the input weather and the field conditions, this could be visualized, aiding in near real-time operation optimization, as well as the long-term planning activities. So I think in summary, I have introduced our recent work on 5 commonly used fire danger indices based on regional climate model simulations and also high resolution observational data sets. Our studies clearly shows indices that consider relative humidity perform better than those which do not. But for predicting severe and large fire danger, wind speed needs to be factored into the assessment. However, this is one variable that regional climate model doesn't do very well either. So we further constructed a linear model for predicting fire size, which performs the best for regional scale fire projection with larger uncertainties when we apply that to smaller scales. Future projections suggest drastic increases in fire occurrences frequency and expansion into regions currently dubbed as low fire risk zones, such as Midwest and Southeast US. So especially we project that Southwest and Southern Great Plains and Florida will see a 2 months longer fire season by the end of the 21st century. Our ongoing and future work is to incorporate power outage and other human-induced ignition and practice into the projection of wildfires for utilities. We're also interested in looking to using machine learning approach to include more input variables, not just the local variables, as well as the teleconnections. For example, the sea surface temperature anomalies into the projections of the wildfires. With that, I would like to thank you for listening, and also my funding agencies, and take any questions if you have. Thank you.
Okay, thank you so much, Yan. I think E.T. had a family obligation, he needed to leave. So thank you for your nice presentations. I would like to open the floor to questions from audience. And please feel free to unmute yourself and ask your question. So.
Yeah, this is Lawrence Boucher. Very nice presentation. Thank you, Dr. Feng. It looked like your future increases seem to be largely over Texas. Is that because the Western US already has a very high incidence in terms of number of days, in that it isn't occurring right now so much in that extreme area?
Yeah, so that's a very good question. I have to say, this is a little bit surprising to us as well. So first of all, in particular, Texas, southern US, it's for the large extreme values, and for the median values, and there's a broader increase over larger areas. And for the western part of the country, one of the reasons we don't, in our calculations, we don't see that drastic increases, partially because we didn't account for the changes of the fuel loadings. Because this is based on the regional climate simulations, we only account for the weather variables in future climate projections. So we don't have the estimates of the fuel availability changes in future climate scenarios. So that's a factor that is not being accounted. So that may affect the western part of the country, because there's a more, I mean, it's more perhaps a few limited region compared to the southern part of the US, like Texas. So that's one reason we think. In terms of the weather changes, yes, definitely we have seen bigger changes, especially like precipitation over the this region, Midwest, and also Texas, that the precipitation is projected to decrease a lot. So that is part of the reason for we see a strong signal that's being populated into the calculated fire indices as well.
Yeah, so thanks for touching on that, because that was going to be my next question, whether this was one of the more sophisticated fuel sensitive indices or one of the non-fuel sensitive. What you might think about doing is, for the variables that you don't have future information for, like the fuels, simply use present day fuels and use your better index.
Oh, that's what we did here. I
Oh,
probably
you did that. Okay.
Yes. So we did. The problem is because we're looking at the changes. So for this ERC, let me see whether I can find that. Yes. So for this index, we do account for the live fuel and dead fuel moisture changes. However, when we calculate the differences, we use the same prescribed fuel on the ground.
Gotcha. Okay.
Except that moisture changes based on it. Yeah.
All right. All right.
Okay.
Thank you.
Uncle, do you have?
Yeah, thank you. Very nice talk, Dr. Feng. I have a question regarding the potential for including ignitions in this, in particular with lightning ignitions. In some areas of US, lightning ignitions are responsible for 50% or even more than 50% of significant wildfires. So is there a way to include that information?
That's a great question. Definitely ignition is very important for the fire occurrences. In our model, no, we don't have that accounted. So we only predicted the fire danger potential. So the triggering of the fire is not included in this method. But the machine learning approach right now we're trying to do will account that in. But for this empirical based fire danger indices, this is only to predict the most likely environment if there is a ignition of fire, and then yeah, what's the most likely to have a fire breakout. So we don't have that ignition mechanism embedded in this calculation, but that's something we definitely wanted to do. We miss the ignition part in this triangle. So we have whether we have fuel. Yeah, we don't have the ignition right now. I think it will be, there are some physically based wildfire models that do account for the ignition, but as far as I know, it's there's a lot of uncertainty, let's just say that.
Thank you.
Also, as Hamid said, I was busy picking up my daughter, but I was listening to you all the way. Great presentation. I have a few questions of my own. So I think you already alluded to some sort of a de-aggregation of the hazard, but would there be any value in kind of looking at wildfires that are taking place at the urban wildland interfaces versus, you know, away from where large populations are? Was that already covered in your analyses, and did you take a look at that?
So our analysis covers the entire CONUS region. Actually, some of my our indices work also include Alaska, but I didn't show that in this presentation. We didn't specifically break it down by woodland versus urban areas, but that's a very interesting direction to go. So I have to say, our regional analysis is mostly based on, let me see, can I find, so our regional analysis is mostly based on the 7 climate zones. So we look at the climate impacts because these 7 region divisions have different representative characteristics of climate changes in terms of temperature and precipitation. So that's our focus. But I think our data set can be used for looking at changes more specifically in terms of woodland and urban areas, for instance, how these trends are changing. It's just different aggregation. It's just different ways of aggregating the data set. I mean, for instance, one of our ongoing line of work is to use the ecoregions to do the regional analysis, but that's more focused on the fuel availability, how that changes region by region. But what you're saying, suggesting, is to look at the urban versus woodlands. That could be a very interesting line direction to do as well. But we haven't done that.
Yeah, my intuition there was, well, okay, when there are people around, maybe we are fighting those fires better or maybe more eagerly than when they're elsewhere. And then therefore, is there some sort of a like a regional or, you know, interface bias between those two regions or something?
Yeah.
But yeah. So is it possible with your framework to, for example, simulate the consequences of land management policies? Like if some political action is taken and this is the way now the land is being managed, what will be the difference in the future? Is it possible to
incorporate that? That's an interesting thinking. I think, yeah, perhaps we can use that land cover changes to customize our fuel availability. I mean, actually, the earlier question is we didn't do that for the changes of the fuel, but maybe we can use the land cover and land use change data to customize the fuel changes in the future. I haven't thought about that, but I think sounds to me it could be done, because basically we prescribe the fuel type based on a database. So if we know the land use, land cover changes, we can modify this map for future scenarios. Yeah, I think it's possible.
And also another question I have is about your temporal and spatial scales. Like when you're, for example, getting information from your neighbors for this point, you go out to the whole US, it's going to bias. The fires in the Midwest, you know, obviously are not going to be well correlated with maybe in the West, et cetera. And you've already kind of, you know, reduced your regions. What about the temporal scales? I mean, if we are going through some sort of a change of regimes in the wildfires, then looking too far back to adjust our models may not be the right thing to do. And maybe you've already covered it. This might be a very naive question, but like if there was a fire yesterday and I was like looking at that at only a data point, then I'd say, okay, the wildfire probably tomorrow is 100%. If I went back the whole year, of course, I get more reasonable. But if I wait 1,000 years, well, what happened 1,000 years ago? Should that, you know, influence what we predict today?
Yeah, I see what you're saying. Yeah. So the spatial temporal correlations that we are doing are point by point. That means we look at the current condition, current location. There is no time lagging in our analysis of the correlation between the observed fire size and the weather conditions. So that is something I think we can use the machine learning approach, because then we can take in not just the local. What I meant local is not only spatial local, but also in terms of time. Right now, we are also using local values. So if we use machine learning approach, then we can use a time series of data. You can go back to 1 week. Maybe that's most relevant. And you can also account for the adjacent area conditions that can affect the specific location of your interest. So that's why, yeah, that's something we're hoping to do with the machine learning approach, which can take into consideration of a much larger array of input variables. So right now we're just using points, the local values for both space and time. Yeah, did I answer your question? I think that's what you're asking.
Yeah, I think you answered my question. I have more questions, but let me just kind of yield a little bit to see if anyone else has other questions.
Sure.
well, one question, let me ask then, I have is that when you have, for example, a model like a normal distribution, is there some sort of a hypothesis testing whether that distribution function is the appropriate function for modeling this phenomenon? And I'm asking because I think as the wildfires are increasing in intensity, the normal distribution may not be the right one, because maybe you have these like a front-loaded normal distribution. I don't know what you call that distribution, but like you have like extremely large fires and then it tails off. You don't have like super large because they're not physically even possible anymore. You're just kind of piled up at the high end.
Yeah.
I wonder whether that's an issue or.
I think it will. So we don't assume anything except when we do the statistic significance test, we assume normal distribution. Otherwise, we don't assume any normalized distribution in our calculation. So yeah, so that might affect our calculation of the significance level. Yeah, so I think that would actually the significance level, we tried a few approaches to indicate that. And for instance, the interannual variabilities in the historical runs are different from the interannual variabilities in the future runs. And that also changes the distribution of the significance level. Yeah. Yeah, I think it will affect, it does not affect our calculations in a sense, but it does change the, what areas the results are significant.
Now let me ask a couple, one logistical question. I think with the time is up. I don't want to keep you too long, and maybe in a follow-up meeting we can ask more, but what is the size of your operation at the national lab there? Is it a long-term objective to pursue this topic at the Argonne National Lab, or is it dependent upon the current interests of, for example, a couple of research scientists there? What is the projection of effort in this area by the lab in particular?
Oh, that's a tough question.
It's an important problem, obviously. It's going to be here to stay. We are definitely suffering a lot in California.
Right. So I think there is a increasing interest from the high level at DOE across different offices, like Office of Renewable Energy, Office of Electricity, and even Office of Science. We all have interest in wildfires research right now. But down to the specific lab, like my lab right now, this project is funded by our lab development funding for the last 2 years. We also write proposals in order to get funding to do this line of research. So I would say that there is a strong interest from the high level of DOE offices, multiple offices, but whether it will be, for Argonne to do or for other national labs to do, that's up in the air. We have to write proposals too.
But Dr. Feng, this is Ari Mosde. Very, very nice talk. I enjoyed it.
Thank you.
But I think I'll follow up on the question. You get funding mostly as a Department of Energy lab, right? So your funding is DOE mostly.
Yes.
On this area.
Yes.
Yeah. Okay. Yeah. All right. Thank you.
All right, I think we reached the end of our meeting today. Thank you, Dr. Feng. This was fantastic work, and you have done a great job in explaining the details, very effective. So hopefully we'll hook up again soon with a group of us and ask you some more detailed questions. I hope you can join us then.
Sure.
I will probably send a follow-up email very soon to set something up.
Okay, sounds
okay.
good. Thanks for your interest. We'll keep in touch then.
we will definitely be in touch. Thank you so
Thank you.
much.
Bye.
Let's thank our speaker, a virtual
Yeah,
or Google
thanks.
Collapse. Yeah.
Okay,
So
bye.
much. Bye-bye.
Bye-bye.